Okay, so what I'd like to talk about today is the problem, start out with is the problem of the day. And on the problem of the day, last class we introduced what graph data structures were. We introduced adjacency matrices and adjacency lists. And getting, again, what was an adjacency matrix? An adjacency matrix was an n by n array such that element ij is going to tell you the true or false of element ij tells you whether edge ij is there, right? An adjacency list was an array from 1 to n of linked lists such that an edge ij is going to appear on the ith list and in the jth list as element I, right? So to represent an edge ij, it's going to appear j is going to be on the ith list and I is going to be on the jth list. Any questions about that? There is another rarely used data structure, but one that we will actually talk about at the very end of the semester, that I'm using here not because it's important, but because it's an example, called an incidence matrix, where an incidence matrix is going to assign every one of the edges from 1 to m a number, okay, and represent the kth edge. It's an n number of vertices by number of edges matrix, such that if the kth edge were edge ij, in the kth column of the matrix, element I is going to be 1, and element j is going to be 1, and everything else is going to be 0. Does everybody get an idea of what an incidence matrix is? Okay. You may say, why do we care about that? And there's not a great reason I can tell you now. There's a little reason I'll tell you at the end of the semester, but not a great reason. Any questions? Okay. It's another representation of a graph, okay, as a matrix. Okay? And your job now is to basically show me how to give an efficient algorithm to convert from an adjacency matrix to an adjacency list. Okay? How do we do that? What is the algorithm to convert from an adjacency matrix to an adjacency list? Okay? How would we go about doing that? Yeah? It's going to go something like, you're saying for I goes from 1 to n, for j goes from 1 to n. That's what you're basically saying by loop through it, right? And now what are you going to do? Well, it's a question of whether it's, I said it's undirected, you could limp through half. Okay, fine, let's not worry about that. What is the main thing that we want to do here? If m sub ij equals 1, then what do we want to do? We want to add a node, you say, to the linked list, or equivalently, what you really want to do is add edge ij to the graph and add edge ji to the graph, I guess if it's undirected. Is that basically right? And again, we might want to be clear that we want to insist that how are we going to handle the fact that you were telling me that it was undirected. Let's think what we're doing here. There's actually an interesting question. If I do it like this, as I did explicitly, where I go from 1 to n and 1 to n, and then add both ij and ji, that we agree is going to add each edge twice, right? And each edge is going to appear twice on the linked list, right? How can we fix this? We can fix this a couple of ways. One that you said is only go through elements where, let's say we do this. One way to fix it would be to have it go from I plus 1 to j, right? If I fix this loop as only going here, now I'm only going through each pair once. How many people see what I'm doing? They're the ones up front who can see, okay? How many people in the back can see what I'm doing? A couple people. Okay, good. Okay, any questions about that? Yeah?
Why can't it just be a for loop to n over 2? Only n over 2, since it's undirected, like you said?
So one possibility, you say, well, we say for it goes n over 2, it would be wrong to have this just go to n over 2. Why is that? There could be an edge from vertex n minus 1 to n, right? There's no reason why there can't be a vertex from n minus 1 to n. Does everybody agree? See that? If I just had the loop go from I goes from 1 to n over 2, I would certainly never pick up that edge. Does everybody agree? Okay. What I could do is, like I say, if I have it go to I goes from 1 to n minus 1, assuming it's one of these, it's not, let's say assume it's a simple graph, so I don't have to worry about self-loops. I could have I go from 1 to n, and I could have j go, I to n minus 1, 1 to n minus 1, j go from I plus 1 to n. And now all pairs where I is less than j are being constructed. Does everybody see that? And if I do that, now I'm only visiting each undirected edge once, and I'm inserting both copies. That would be a perfectly fair way to do it, right? An alternative way that would be fine, I guess, would be to have it still go from 1 to n and not insert that copy. Does everybody see that would also work, right? You see what the problem is? I don't want to insert two copies into my linked lists of an edge ij. Okay, and this is how I avoided that. Any questions? And what is add doing? Here what I'm assuming, let's just now be a little bit more precise. Before I call this, I had better init my adjacency lists. Okay? Meaning I took my array of from 1 to n of adjacency lists and set them all to nil, right? Because originally the adjacency list data structure had better be built from nil records, empty lists, right? And then what I'm going to be basically doing in each one of these insertions is add ij is going to say go to the ith list and add j to it. Perhaps inserting it at the beginning of the list would be the simplest thing to do. Any questions about that? Any questions about how I constructed my adjacency list from my adjacency matrix? What is the time of this algorithm? If I have n edges and m edges, what's the time complexity of this algorithm? Yes? What? It is order n squared. And why is it order n squared? There's the outer loop here, and then I'm doing a constant amount of work for every edge, right? There can't be more edges than n squared, so everything is okay. Any questions about this? Fine. Now I want to go from an adjacency list to an incidence matrix, okay? And what am I going to do? This is a little bit, there's a couple different ways I can do this, but does everybody see what I kind of want to do? I want to assign every edge a number from 1 to m and use that to describe the, and have that column, the ones in that column will describe the endpoints of that edge. Okay? Any questions about that? How can I go about building this matrix from the adjacency lists? Okay? Any ideas? What kind of a procedure? Yes?
So first, you have to initialize an n by n matrix.
I have to initialize my n by m matrix, so I'd better figure out how many edges there are in my graph, right? Does everybody agree that if I'm going to fill an n by m matrix here, I am going to have to know the number of edges in my graph, right? And maybe I had a count of that in my graph data structure, or maybe I have to go count that explicitly, right? Does everybody see that? How would I figure out how many edges there are in a graph specified by an adjacency list? How would I do that? Yeah? I could just go 4i goes from 1 to n. While the list is not entry, count how many total list entries there are. Divide that by 2. And that should give me, assuming it's a simple graph, divide that by 2, that'll give me the number of edges. Any questions about that? So it should be clear I can now construct my matrix of all zeros, that of the right size, n and m. Now, what am I going to do? How can I go about filling this matrix in? Okay? Yes?
You could go through the list every single time you see an I connected to a J. That's one edge, and then you go to the next edge.
Right, so basically what I need to now do is to go through my adjacency list and figure out whether or not, basically, I am coming up with a new edge that I haven't seen before, right? And then when I see a new edge that I haven't seen before, fill in the appropriate bits. Does everybody agree with that? Yeah.
To make sure that you're not adding the same edge when you have to like search either the matrix that you already made, so like it'll take like.
Okay, so there's a concern here. How do I ensure, as I cruise through my adjacency list, how do I ensure I don't add a column for edge ij and edge ji? Right? Yeah?
So like either you can search like say for the two vertices and like search across on all the edges, or you can just delete it from the adjacency list.
Okay, so how would I do this? Let's think about it. One way I could do it is I come up here on list number 1, and I see 3, and I ask myself, is 1, 3 already in the matrix, right? Well, how would I tell that? Yeah?
Yeah, we can simply go through whether list I and scan for j, right? So if j is greater than I, it is not in the matrix.
Does everybody see that if I adopt the convention, so long as j is bigger than I, this is the first time that I've seen it. Okay? This is easier than going to search for it explicitly. Does everybody see that? Suppose, let's say that my list here, the fifth list, was 3, 7, 1, 4. How could I make sure I only add the appropriate edges? If j is bigger than I, no. Is j bigger than I? Yes. Did you see that if I just do the test, is j bigger than I will see each edge only once. How many people see that? Okay? So now, what does this algorithm look like? It's sort of like I claim going to be the following. Let me now erase this and put my own thing. I would probably say that it's going to be looking like it's going to be count the number of edges, m, the number of edges, initialize the n by m matrix, right, that I want to fill in. I'm going to let k equal 0. K is going to be the number of edges I've already put into my matrix. Okay? Now I want to cruise through my adjacency list. It's going to go something like 4i equals 1 to n. Now I'm cruising down this thing, bop, 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 bop. And inside here, I'm going to be, while, L is not equal to nil, while I have not hit the end of the appropriate list, if j is greater than I, okay, now I have discovered a new edge, right? And what am I going to do with that? I'm going to set, if this is my new matrix here, let's call my incidence matrix big I. I'm going to be setting I of k, comma, little I equals I sub k of little j are both going to be equal to 1. Does everybody see that? Once I know what my two i's are, I'm going to set the kth ith element 1 and the kth jth element 1. Okay, and now and then I'm going to go and bop up k equals k plus 1, right? Okay, any questions about that? Yes?
So I'm not getting the 1 and 3. That's if the nodes are
Okay, so what is this saying here? Again, remember that in an adjacency list, let's remember what we've got. The main structure is an array of linked lists, right? It's an array of size n, the number of vertices in the graph, of linked lists. And each linked list element is going to have two fields. One is a pointer to the next element, the other of which is the pairing vertex of I, the number that with I defines an edge, right? And so what I'm going to do is now walk through this list and look at these j's. If j here is bigger than I, it's the first time I've seen that edge of the two copies, right? So let me add it, okay? And otherwise I don't add it. Yeah. What if they what? They weren't integers. They shouldn't be in your graph, right? This is a structure you built to store a graph. It's an adjacency list structure to store the graph. And the fields that we care about, the field that we care about is what is the other vertex of the edge. Okay? So if we're assuming, we're naming the vertices names 1 through n, integers, okay? And that's going to be the name of the vertex, and therefore the name of an edge is going to be ij, a pair of integers. Does that clarify it? Any questions like that? Yes? So what is the time of this algorithm? Let's think about it. Any questions about what this algorithm is? How many people sort of see what I've been doing? And how many people don't see what I'm doing? Okay, a few who will admit it, okay? Any questions in particular? Okay, what is the running time of this algorithm? To count the number of edges in the matrix, if we had an adjacency let's say I had an adjacency list and I wanted to figure out how many edges were in there. If I didn't store it, how much time would that take? If I have an n vertex graph and with m edges, how much time will it take? It will take mn, not m what n? Plus n. It will be order n to walk down this, and a total of 2 times m steps down lists. Does everybody see that? The time it should take is something like n plus 2m, or big O of n plus m. So counting it is going to be order n plus m. How many people see why counting the number of edges in an adjacency list is n plus m? How many people don't see it? If you really don't see it, hold that hand high, because this is the kind of thing that you need to do to be able to work with these lists. Okay? It's order n, because we have to walk down and say, is this list nil? Is this list nil? Is this list nil? It's order m also, because we have to walk to the end of all these lists. Okay? For every edge, we're going to walk over it twice. That's why I got my n plus 2m. Any questions about that? Okay? This is important that it doesn't have to be important today you come out of this solid. It's important that before next class you come out of this solid. Okay? Because we're going to be working with these adjacency lists. They're not that hard to work with. But you have to make sure you understand what the structure is. Any questions? Okay? Yes? Well, I haven't gotten to the initialization. Now the second line is initialize my matrix, my n times n matrix. This is a times, not a plus. What is the cost of initializing my n times n matrix? That is n times m over here. Does everybody agree with that? How much time does it set to take k equal to 0? 1 step. That one's easy. Okay? I've got 4i goes from 1 to n. That means it's n times whatever's going to happen here. And what is this? Well, now I'm basically walking through the edges of my adjacency list, right? For each one, I'm going to test whether I is less than j, which takes constant time, and then set 2 elements of the matrix together. How much time does this bookkeeping take for testing whether I is less than j, and if so, setting the right numbers? How much is that if statement? Constant. Now here, the only thing that's a little tricky here that you have to see is I say to go through the adjacency lists, I go 4i goes 1 to n while the ith list is not empty, right? How much time does this while loop take? Takes at most n, okay, on each iteration. It takes the degree of the ith vertex, right? That would be another way to say it, right? And here we've got to be a little bit careful with our analysis. If we say the degree of the ith vertex is at most n, going through an adjacency list we're saying is at most n times n, it's big O of n squared. That's true, but that's a soft analysis. Does everybody see that? If the degrees of the vertices were very small, we're only going through with the degrees of the vertices. Really what this time is going to be, this total number of times the while goes through is the sum of the degrees of the vertices, which is twice n. Twice the number of edges, twice m. So the total amount for these two loops is going to be order m. Okay? Any questions about that? I've done a little sleight of hand here, but this is important to see. Okay? Okay, what am I saying here? Let me go to another board because maybe it's getting too messy here. What is the time it takes to walk through an adjacency list? That's really all that I was doing there, right? I was walking through the adjacency list. And how do you walk through an adjacency list? The basic paradigm or pattern or whatever language you guys use. 4i goes through the number of vertices, right? While the list L sub I is not equal to nil, right? We're now going to walk through the ith list. We're going to then do something that takes constant time, right? What is the time complexity of this idiom that says 4i goes through the number of vertices, while j goes through the number of edges on the ith list? The total time for these two nested loops is order n plus m. Okay? You may say, hey, why isn't it multiplying something? I always multiply something. It is multiplying something, but let's look what we're multiplying. What's the length of the ith list? If we say that it's order n, because every vertex might be adjacent to every other vertex, we are overcounting. Does everybody agree with that? What if we instead say that on average, it was the average degree of the vertex? Right? Some vertices are going to be high degree with n. Some of them are going to be very low degree, maybe 1, right? The average degree per vertex times the number of vertices is going to give us what? Basically twice the number of edges. Okay? Do people see that? Let's take a look at it. Again, maybe you don't see it yet. What if we have a graph? Let's take a look at a graph here. Chung, chung, chung. Here's a graph, right? What's the degree of this vertex? 4. This vertex has a degree of 2. This vertex has a degree of 2. 1, 1. What is the average degree of a vertex here? Somebody come up with it. What's the average of this? Hopefully this is 8. This is what? 2. Okay, well what is it? If we add this up, it comes up to be what? 12? 12 divided by 6 is what? 1, 2, 3, 4, 5. Wait a second. What am I doing wrong? It's 10. Okay, good. 10 divided by 5 is equal to 2. Does everybody agree with that? And what is this sum? This is twice the number of edges. 1, 2, 3, 4, 5. Yeah, that's right. Why is it twice the number of edges? Because every edge is getting counted once on the degree here, and every edge is coming out twice, is getting counted once here. Does everybody see that? Suppose we had a bell on that door that, let's say, every time someone went through it, went ding. And I wanted to find out how many people were in my class. What would I do? People are going to walk in. Some people are going to get bored and walk out. Some people are going to come in late. I'm going to hear ding, 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 ding. Every one of you will ding the door twice. Does everybody see that? If I counted the dings and I divided by 2, I know how many people there were, right? If I sum the degrees and divide it by 2, I get the number of edges. Does everybody see that? So if we think of this, what's the average amount of time that the while loop is going to go through? We agree that that is the average degree of the vertex. Does everybody agree? So think of this idiom. For I goes from 1 to n, while to the end of the ith loop. The total number of steps in this is going to be n plus m. This is going to be what drives us in here. Okay? Any questions about that? Yes? So you're saying, is it an expected complexity? The answer is no. Okay? This is an exact thing. I'm trying to simplify the question is, how do I look at this code and figure out many steps it's taking? Right? This is really right now what we're talking about. I look at a piece of code and I want to say, how many steps are it taking? Now, you guys have all been programmed to say, a worst case upper bound for a program is I take for every loop, what's the maximum number of times it can go around? Okay? And I multiply them. And that gives you an upper bound. But sometimes, when you look at this thing, that upper bound isn't really realized. Okay? And let's look at this again, what it's doing. I claim that in an adjacency list, okay, the number of times, what's the total number of steps that's going to be done walking through all of these lists with this code? I claim you're walking over every edge twice. Does everybody agree with that? That what are you doing? You're going for I goes from 1 to n. Once you get to a list, you're going bunk, 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 bunk. The next list, you're going bunk, bunk. Next list, you're going bunk, 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 bunk. What is the total number of bunks by the time you hit the end of it? You could say, well, I'm doing at most n bunks per iteration, and there's n iterations at most n squared bunks. And you're right. But I'm telling you there are exactly 2m bunks. And that is also right, and a smaller, not potentially smaller number. Does everybody see? If it's a sparse graph, 2 times m is the smaller number. So it's the more interesting analysis here. Okay? Does that answer your question?
Yeah, that makes more sense.
Any questions about this? This has to be clear because this is why adjacency lists are a great thing. If, in fact, we always walked over all n possibilities, everything is going to be n squared. Okay? If everything that Facebook had to do with its Facebook graph was order n squared, where n is the number of people who have Facebook accounts, Mark Zuckerberg couldn't survive, right? Because 6 billion squared is too big a number, right? But because Mark Zuckerberg represents his graph, Facebook, as an adjacency list, what do we know? We know that whenever he wants to go through and says, counts how much money he's making from each one of you, how's he going to be, or every friendship, let's say he wants to count how many friendships there are. He's going to go bunk, 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 bunk. His time is going to be the sum of the degrees of each vertex. Okay? Which is the same as being n times the average degree per vertex. Isn't that right? If I say, what's the total of these numbers? Isn't the total, if I give you n numbers and I say, what's their total? Isn't the total of that also really n times the average? Okay? And that's all that I was doing in my analysis. That is why these two loops, think of them as n plus m. Okay? Any questions about that? Yes?
So it's not like we're traversing that list n times. It's just
You're not traversing that list n times, you're traversing each of the n lists once. Okay? That's the important point. You're traversing each of the n lists once. Okay? Any questions? How many people see why this metaphor up here, for I goes from 1 to n, while the ith list is not nil, why this is an n plus m algorithm? How many people see it? How many people don't see it? Okay? This you got to see. There's a few things I'm going to say you got to see. This you got to see. So if you don't see it, get help. Okay? Any questions about it? Yes?
Is the reason you have to be care of the capital M because some of them might be empty and you have to waste time looking at empty?
The question is, why do I worry about the n plus m instead of just saying, oh, m is bigger? Let's say we had Facebook and we go to a country where nobody has any friends. Okay? Now, what is this Facebook graph going to look like? There's going to be n people all eagerly registering for Facebook, and then I don't know what they're going to do there. But does everybody agree that that graph is going to look like as n empty lists, right? How much time does it take to count the number of edges in n empty lists? N. Does everybody see that? How much time does it take to count n empty the size of n empty lists? It's n, it's not 1, right? Because you got to verify, is this guy really empty? None of them really have friends in this country? Okay? So because m can be smaller than n, I write that as order n plus m, just to cover my butt in case they don't have very many edges. Any questions? Yes? You have to initialize the matrix to, it's going to be n squared, okay?
So we can always assume that it's not initialized, right?
Well, you shouldn't assume it's initialized. Someone gives you a chunk of memory on the, says, hey, here's a chunk of memory. How do you know that it's initialized? You've got to initialize it, okay? And that takes order n squared time to make sure. Otherwise, someone could have randomly filled in friends for you that you don't have, right? Any questions? Okay? Any questions about this? So now let's get back. What was the time it took to turn an adjacency matrix to an incidence matrix? We said this for I goes from 1 to n while j goes, the list is not empty. Do something that takes constant time. This I read as n plus m times 1. So I have n plus m times n times m, n plus m plus n plus n times m plus 1 plus n times plus m. What is the sum of those things, big O-wise? N times m. Does everybody see it? Okay. Any questions? And the last one, convert from the incidence matrix to adjacency lists. How would I go through the incidence matrix and convert that back to an adjacency list? Okay? What do I have to do that? If someone gives you an incidence matrix, what would you do? Yeah?
Go down the edges and see which nodes they connect, and then input the two nodes as being connected.
Right, so it looks like what you're probably going to do is something that looks like this. It's going to be the init my adjacency list. How do I init an adjacency list? Okay. What?
Make the pointer to null.
For I equals 1 to n. Okay. L sub I is equal to nil, right? So I initialize it to be nil, right? Now what I want to do is to cruise through my adjacency incidence matrix. What am I going to do? I'm going to say for I equals, or let's say x, k. I'm going to reverse it. For k equals 1 to m, right? I am now going to walk down through the edge here and figure out for I is equal to, let's say, let's say j. Well, okay, for, let's say, some other variable x. X equals 1 to n. If element kx is equal to 1, then I've got one of the two endpoints of that edge, right? Keep going. Next time I see it, the second one is going to be the other endpoint of the edge, right? Call this I, call this j. Okay? If so, now what am I going to do? Insert edge ij and ji into my adjacency list, right? So this is going to be a 4k goes from 1 to n. This is going to be a 4x equals 1 to the number of vertices. Scan through, and basically if element I, k, x is equal to 1, store it as either I or j, okay? And then at the end set, basically add the edge ij and the edge ji, okay? Any questions? So this is going to go through, this loop goes through m times. The inner loop goes through n times. This stuff in here of testing whether this is true is a constant amount of work. So this is going to be an order n times m algorithm. Okay? N times m. Any questions? Okay, any questions about these? Okay, yes?
Doesn't it sort of, for all these, incidentally end up being just the initialization time for
So what you notice here is, hey, none of these algorithms look that complicated. All of them are being bounded by the time it takes to initialize the thing. And the wonderful thing about graph algorithms, the good graph algorithms are going to be basically time order the initialization of the data structure. The amazing thing about, many of these graph algorithms is they can run in linear time in the size of the adjacency list. Or if you're really stuck using a matrix, it's going to be linear in the size of the matrix, but that's n squared. Okay? Any questions here? Okay? Any questions about working with these data structures? Yes?
So regarding the space complexity, which is better, the n by n matrix or the list?
Which is better space-wise? The n times m matrix or the adjacency list? Let's put it to a vote. Which is better? The adjacency list representation of a graph, which uses less space? The adjacency list representation or the incidence matrix? Who here says the list is more efficient? Who here says the incidence matrix? Yeah. Yes, obviously, this is less. This is n plus m. This is n times m. Okay, n times m is bigger than n plus m. Okay? Any questions? Yes?
This one you're storing like bits, the other one you're storing like numbers.
Okay, let's say in a world where we're assuming that we're storing them all in one unit thing, and we're not worried about bits, but we're worried about the number of integers we're storing, it's the same thing. Okay? Any questions? Okay? Good. Okay, fair enough. Okay, so what I would like to now talk about is the simplest thing is to read and write a graph. That's what we have now done. We know how to store a graph. We know how to read and write it. The second thing that turns out to be very fundamental is to be able to walk over a graph and visit each vertex or edge in a logical order. Okay? And so there's this problem of traversing a graph. Okay? And to traverse a graph, we need to be able to do the following kinds of things. We want to walk over the structure of the graph in such a way that we're efficient, meaning we don't visit any edge or vertex more than we have to. And we're correct in that we always visit every edge and vertex of the graph. Okay? This is what a traversal involves. It involves taking a structure of a graph, let's say like the maze of this room. If you think of it, there's all kinds of paths here that I could walk on, right? Suppose you wanted to program me to make sure that I could leave the room. Okay? I've got to find a way to walk over the graph of this room, the network defined by all the paths I can walk on, pathways I can walk on. If you want me to guarantee I can find my way out of a maze, you've got to guarantee that I can visit will have a way that I can visit every vertex in the graph, an edge in the graph. Okay, so I don't miss the door, because it's going to be someplace. but I do it in an efficient way where I don't get trapped visiting the same thing over and over again. Does anybody know an algorithm for getting out of a maze? Okay, it's a very subtle thing. How do you get out of a maze? Just put your right hand on a wall and walk around, right? Does everybody see that if you put your right hand on a wall, okay, and you want to get out of a maze, you can put your right hand on a wall and guarantee that you're not going to repeat anything before you have explicitly visited the entire maze. Okay, does everybody see how I'm going to find my way out of the room? By following the right-hand wall. How many people see that? How many people don't see that? Because I'm not getting out of the room. Okay? Does everybody see that? Okay? The lesson here, you've heard this notion that, oh, you follow the right-hand wall and you get out of a maze. Use this as an example of the fact that these traversal algorithms, there's some subtlety behind it. Okay? That you made some kind of assumptions about the structures of mazes in order for that rule to work. Okay? But for a general network, to have an algorithm that has the property that it doesn't get into loops of visiting everything again and again and again and again, and yet visits everything, is a subtle problem. Okay? Any questions? Are people convinced that it's more subtle than maybe it might have seemed from the maze example? Any questions? So we are going to talk about a approach. Actually, there's a nice link there if you want, but I'm not going to do it because we're running a little low. Okay, what I'd like to talk about here is now the basic idea for how we traverse a graph so we're guaranteed that we're going to get out of any maze. Okay? How is it that people get out of mazes? Okay, you've heard the one about the guy who I guess left the string behind him, right? Or they dropped breadcrumbs behind him. Okay? How many people have heard that myth, right? There's one of these myths about it, right? The breadcrumb guy had it right. Okay? What is the idea? By dropping breadcrumbs in the maze, or equivalently by marking vertices in a graph when we visit it, we can keep track of where we visited. What was the problem I had walking around here? If all I am doing is hugging this rail, I have no memory of when I visited a vertex before. Does everybody see that? Okay? So we need a way to remember we visited something. So in my implementation of breadth first search and depth first search, I'm going to maintain each vertex in one of three states. It is undiscovered, meaning nobody knew about it. I haven't seen it yet at all. Another state is I have discovered it, but I haven't finished doing everything I'm going to do with it. The other one is processed, meaning I have completely visited all the edges associated with this vertex. This vertex is no longer of interest to me, and I'm never going to visit it again. Any questions? So the key idea in our traversals is maintaining the state about the vertex. Any questions? Okay, and again, there's going to be a state of traversals. We go from undiscovered, meaning, oh my God, there's a spot in the maze, to let me explore this edge instead of going this way. That means I'm now processing it. To I've checked that place out, I've checked that place out, I've checked this place out. None of them are any good. That means I've completely processed it. Yes?
So we're saying we need order and extra space to traverse a graph.
So I need, according to this, a data structure that is going to be order n, the number of vertices, in order to traverse the graph. That is true. I'm going to add another data structure to do that. Any questions? In fact, I'm actually going to add 2 or 3 data structures to do it. Okay? But they're all going to be order n, the number of vertices in the graph. Any questions? Okay, good. The other issue when exploring a graph is I'm going to maintain a to-do list. Typically what happens in a maze is I come here and, oh my God, I can go that way or I can go that way. How do I want to get out of it? Okay? What I need to do is to say, okay, I know there's a way to go there. I know there's a way to go here. I'm going to go this way. Okay? But I'm going to remember that there's this other path that still exists, right? So when I get stuck and I don't know what else to do, I'm going to wander back here and explore that. Does everybody see that? So I need to have a to-do list for dealing with it. Okay? And so initially my to-do list is going to be, I'm going to start from a particular vertex of the graph. I'm assuming there is a graph. I'm assuming you're going to be giving me a start vertex. Typically, the start vertex is vertex 1 if you use one of these adjacency lists. Or maybe they're going to want you to say, do a search from vertex I. But typically, you've got a graph, you've got a start vertex, and you want to explore the graph from there. Okay? And what is the basic paradigm? Okay? The way that we're going to look at it is to explore a vertex, we're going to take an edge out of it. If that vertex was never discovered before, congratulations, I discovered you. Okay? And now you have been discovered. I will be forever remembered as the discoverer of you. Okay? And you now are marked discovered. Before you were undiscovered, now your status has changed. But maybe now I'm going to do other things and explore other things. But once I discover you, I'm going to toss you in a data structure to process you later. Okay? Any questions about that? Okay? And that's basically the model here. Okay? So what is the idea of why I know I'm going to get out of my maze? Okay? If I have a graph and I do this kind of traversal. Starting from here, I am going to look at all possible moves. I discover that I can get there. I discover I can get there. I discover I can get there. The things I discover, I put in my work to explore more. Right? I'm now going to continue to explore one of them. And maybe I decide to explore this. Maybe I've already discovered that possibility before. But I didn't discover that possibility. I didn't discover it. We're going to explore all of me, everything I can do. Whenever I discover a vertex, okay, I'm going to put it on the list to eventually explore deeply. Why do I know I'm going to get to that door if there's a way to get to that door? Well, that door is going to be, if it's connected to the graph, there's going to be another vertex to it. And if the whole graph if there's a connected way from me to here, it's going to be reachable by something I explore, and something you explore from that, and something you explore from that. Okay? So long as I keep track of everything that was visited and eventually explore all possibilities on it, I know I will visit everything. Any questions? Okay. Now, breadth-first search, which is the one that we're going to talk about today, is, probably the simplest traversal, or most natural traversal program. What it's going to do is to visit it's going to basically have the property that it's going to visit all neighbors before it visits anybody deeper. Okay? And as we're going to see, breadth-first search has a connection to shortest paths in graphs. You said I needed to use extra storage to tell whether or not the state of my vertex, have I visited it, has it been discovered, undiscovered, or not? The way that I'm going to represent in my depth-first search, again, there's different ways you can write the code and yada yada, but I'm going to represent in my depth-first search, my breadth-first search, the state of what I am doing by 3 arrays. Processed is going to be a Boolean array. True or false, have I been processed yet? Okay? Discovered is a Boolean array. Have I been discovered or not discovered yet? Okay? And parent is going to be the discoverer of a vertex. Does everybody agree that if I am in a graph, if I am walking around a graph, let's try to make a graph here. If I took a look at this graph, okay, if this is where I am starting, and I look at all the outgoing edges, this is the only one that was discovered. As I explore the edges, I'm going to discover this one. Does everybody see that? If I start my search from vertex 5, the first guy who gets discovered is going to be number 2. And who discovered it? Well, it was discovered when exploring vertex 5. So we're going to use this parent directory. The parent array is going to note who is the one that discovered it. Okay? Namely, to discover a vertex, we're going to be walking from one vertex to the vertex that we discovered. Does everybody see that? So when x is discovered, it was done by visiting from some vertex I, okay, to discover x. That if it was used edge ix was what discovered it. So if so, the discoverer of vertex I is going to be x. Any question? Yes?
For process and discover, why do you separate them to Boolean arrays?
I separated them because I thought it was a good idea at a time. You could have had it be represented by some kind of an enumerated type or something like that. I chose to do it this way. You know, this is in the level of programming detail. Algorithmically, however you store it, it's going to be constant information per vertex, right? So if you store it in one variable, it goes from one versus two variables, Boolean variables, it's the same thing, big O-wise. Okay? Any questions? Yes?
Is this going to turn an arbitrary graph into a tree somehow?
Is this discovery is going to turn an arbitrary graph to a tree? The answer is yes. Actually, not really that it's going to turn the graph into a tree. Is it's going to lay a tree on top of the graph. This is actually an important point. There is going to be a tree of discovery in any graph. Let's take a look at it. Let me see if I have a little example here. Kabunk, kabunk. Suppose I were to start from vertex 1. I claim that if I process this, does everybody see that as I do my walk over from vertex 1, every edge is going to get walked over. Every vertex is going to be discovered how many times? How many times can a vertex be discovered? How many times can the telephone be discovered? Once, okay? So what does it mean if we start from one vertex and we discover certain things, and each of these other guys discovers certain things? What does that give us? It gives us a tree. Does everybody see that? So in fact, this is kind of an important. It isn't turning the graph into a tree, but it is saying it is constructing a tree out of the graph. It is sort of taking certain edges of the graph and forming a tree out of them. Okay? Any questions about it? Yes?
Confuse us why 5 was discovered twice.
Was 5 discovered twice? The answer here, as we look at it, is the solid edges in my tree are discoveries, okay? The other things are sort of like being the second guy to discover it. If you think about it, we've got to walk over. This is basically showing the thing on the left is my graph, right? The thing on my right is a visualization of my discovery and traversal pattern. Right? Some edges are going to be involved in discovery. Other edges will not be in discovery, right? But we're still going to have to walk over them. Does everybody see them? If they're not involved in the discovery, that meant they visited a vertex that somebody else had discovered. Okay? So the solid lines here are the arrows representing discovery, and the dashed ones are representing the first time we have seen the other edges. Does everybody see that? Okay. Yes?
Plus also, why isn't there an arrow from 5 to 2?
Why isn't there an arrow from 5 to 2? Okay, so what is this going to be? Let me show you the example. Let me try to execute this example here. If I was going to do breadth-first search, I haven't shown you the algorithm here. But let me tell you how it's going to work, and maybe we can execute it and see what's happening. What we are going to do is we're going to represent our graph as a vertex. And for all the vertices 1, 2, 3, 4, 5, and 6, there's going to be a state of discovery for them. Right? There's a question of have they been discovered? Have they been processed? What is their parent? Does everybody agree with that? Originally, none of them have parents, right? Except once we've decided that we're going to start our traversal from vertex 1, what does that mean? First, our queue of work to be done We're going to use a Q to represent the work to be done. 1 is going to sit on that Q. Does everybody see that? In the course of setting that up, what's the parent of 1? Well, how did we hear about vertex 1? God told us now, right? Nobody discovered, it was sort of creation. So, right? So maybe we'll say it was discovered by vertex 0, okay, which we'll say is God or something. Okay? Has vertex 1 been discovered? Well, once we're told about it, yes, it has been discovered. Has it been completely processed? No. Let's now go through all of the neighbors of 1. Go through the adjacency list of 1 and see what happens. We discover vertex 2. Has vertex 2 been discovered? No, so that's great. Now vertex 2 has been discovered. First, now as I process number 1, 2 has been discovered, so I better put it on the list of work to be done. Has 2 been completely processed yet? No, but since I discovered it, 1 is the discoverer of vertex 2. Does everybody see that? Yeah.
Why did you remove 1 from the queue even though you didn't process all its edges?
So the way that the algorithm will go when we look at the code is, to get started, I start by removing something from the queue and go through all of its outgoing edges. Okay, what is 1's other outgoing edges? 5. Okay, has 5 been discovered yet? No, that's great, I discovered it. I get to put it on my queue. And who's the discoverer of number 5? Me. Okay, 1. Okay, now let's go through I still have another edge, 6. Has anyone discovered 6 yet before? No, so I get to discover 6. Does everybody see that? Now, who's the discoverer of 6? It is me. Okay, right? Good. Now, am I finished processing all my outgoing edges? I am now been completely processed, and I step off the stage, number 1. Does everybody see that? What's my next step? Well, the next thing in the queue is 2. Get 2 outside of queue and look at all of its neighbors. What are the neighbors of 2? 1. 1 has, already been discovered. I don't get credit for discovering it, right? Neighbor 5. 5 has already been discovered. I don't get credit for discovering it, right? 3. 3 has not been discovered yet, right? So now, let's discover 3, and vertex number 2 is the discoverer of 3. Does everybody see that? And now, I have visited all outgoing edges from 2. Does everybody agree? So are we finished with vertex 2? Vertex 2 is completely processed. Any questions? That's good. Now, let's see what goes on next. The next thing I had, 3, when I discovered it, should have been put in the data structure. Does everybody agree? Good. Now 5. 5, look at 5 outgoing edges. 5's outgoing edges are the 1 already discovered. 2 already discovered, right? 4 is a new one, right? So 4 has now been discovered. The discoverer of 4 is 5, right? And now, I guess I also have to visit,
No, this is an extra. You have 7 boxes.
7 boxes. 1. Oh, I see. So this guy's, okay. Okay, trouble. Now I'm confused. But this, okay. Any questions about, was what I had right, or was there a problem? Okay, then let's say I'm going to not keep going. Okay? What is my goal now? I was still exploring the output of 5. Okay, right? I was looking at 5's children. 5 was the one that discovered 4. I had removed 5 from here. I looked at all of its possibilities. I discovered 4. 4 is going to go here, right? The next one I look at is vertex 6. Vertex 6, the only one that it's adjacent to, has already been discovered, right? So I'm not going to discover it. Okay? And does everybody see 6 has been processed now? Some of these other ones, I think I've also processed what? I also processed 5. Okay? What is my next one? Okay? My next one I'm going to do is to pull 3 off of it. 3, I'm going to go visit 2, it's been discovered. 4, it's been discovered. 3 has been completely processed. Now 4. 4, the neighbors of 4 are 3 discovered and 5 discovered. Does everybody see that as of this point, everybody's now been processed? I have my tree of discovery. I have visited every edge, okay? And I now have finished my traversal. Any questions about that? How many people see the algorithm? Okay, well, you don't see the algorithm because I haven't put the algorithm up on the screen yet, but you see the example. Here is the implementation of that breadth-first search that I just did that maybe makes it clearer. What are we doing? To maintain our work to be done, we're using a queue named Q. Okay? What do? We initialize the queue to be empty. We say our start vertex is the first work to be done, and the start vertex has been discovered, right? Now, so long as the queue is not empty, that means I've got stuff to still process. Is that right? And once I have stuff to be processed, I take V off the queue. I set, is it being processed to true? Okay, now V's been processed. I take a look at all the edges out from V. Okay, and for each one of these edges, I ask if for every Y that is on the adjacency list of V, is the edge Y, VY, has it, okay, let's think what we're doing here. VY, I am now going to be looking at, is this the first time I am through my edge or not? That's what this logic is going to be testing. Okay? Basically, if Y had not been discovered before, and now I'm visiting Y, I am discovering Y. So if we go to the second half of the program, what do we do when we discover a new vertex Y? We stick Y in the queue, mark Y discovered, and mark me as the parent of Y. Does everybody kind of see that that's doing what I was doing before? Okay? And that P goes to P.next is just showing I'm iterating through the loop of vertex V. Okay? All the adjacencies of there to make sure I visit all the possibilities. Yes?
So in your code, do you process all the edges before moving through the...
So what is, okay, so the question is, what is this processed thing? Okay? Notice that when I say process my array, that is a Boolean array, have I been processed, right? But I also do something else I didn't tell you. I have this routine called process vertex early and process edge and process edge vertex late. Does everybody see that? What do those routines do? They do whatever you want them to do. Okay? Because we don't visit, why do we do a breadth-first search of a graph? Is it to say because I want a breadth-first search of the graph? No, typically there is an application you care about. Breadth-first search is not something someone is paying you for, right? No one's going to say, Mark Zuckerberg's not saying, do a breadth-first search of the graph, and then a couple of weeks later the guy comes back and says, done. There is something he wants to do on the graph. Maybe he wants to figure out how many people there are with more than 17 friends. Maybe he wants to figure out how many triangles are there in the graph of where I'm your friend and you're my friend and so on like that. Does everybody see that he wants to do something with the graph? The payload that what you're doing when you walk over the graph are these vertices, these functions I have put in this thing, which enable you to uniquely do something before you process each vertex, once when you process an edge, and once at the end of the graph of visiting a vertex. Does everybody see that by adding whatever logic you want there? Let's say your job was to paint the floors of the maze. What would your algorithm be? For what does process edge do in that case? Basically, you want to paint the edge. Does everybody see that? Okay? So if I ask you, give me an algorithm to paint a maze, I'd ask you, what color do you want it painted? And you say, well, pink, and here's the paint for it. What do? I'll say, give it to this guy, have him do execute the breadth first search algorithm. And whenever he gets to call breadth process edge, paint that particular area. Does everybody see that? How many times will any part of the floor be painted? Exactly once. How do we know he's not painting the thing pink over pink? Because we are calling it only once. That's what that logic is to insist, right? We're processing it the first time we see the edge. And let's say they want him to add black highlights at a vertex. Well, maybe the first time, maybe he wants to paint the vertex highlights after he's painted the floor all pink, right? Then process vertex late should be paint the highlights at the vertex. Does everybody see that? There is payload that you want to do, and the payload is being added at by these process calls. And many of the graph algorithms we will come to know and love are basically breadth first search or depth first search with the right payload added at these when you visit a vertex or when you visit the edge. Any questions about that? Okay. This is basically telling you that I want to use those process things as payload for doing complicated algorithms. We'll talk next time about, don't move yet, but we'll talk next time about some of these more complicated, these algorithms where we use the payload, because we don't really have time for that. But we do have time for one thing left. What good is this tree of discovery? Suppose we do this breadth first search. What does that tree of discovery do us? Why did we bother to build it? Yeah? Because it tells us something in a breadth first search. This tree of discovery, in fact, reflects the smallest number of hops needed to discover a vertex. Suppose we start from our source A. What are the vertices that are within one edge of A? They're the ones that are directly connected to A. Does everybody agree that the shortest path to those vertices is the direct hop if it's an unweighted graph, right? And all of those got discovered by it. Suppose I got discovered by a vertex that's a distance I from the source. How far am I from? What's the shortest path between me and the source? I plus 1. Why? Because the shortest path to that guy was I. Okay? Because of the way breadth first search is working, because there is a FIFO queue, it is processing the vertices in order of their distance from the root. That's kind of the interesting thing about the queue, right? If we have a graph and we're starting from a particular vertex, what does the queue look like? I mean, what's going to happen if we start from this vertex? We visit all the edges that are within one of it. Then the queue is going to start to expand and visit the edges, the vertices in this order. And then it's going to expand out like this. Does everybody see that because breadth first search uses a FIFO queue, we're processing the oldest vertex before we process new vertices? Does everybody see it? The vertices are getting processed in the order of how close to the root they are. So the interesting thing about the parent is that the parent defines a tree of discovery. And so the problem of what is the shortest path between any of you and the root, okay, how do you do that? You find for you what is your parent, and what is his parent, and what is its parent, until you get back to me. Does everybody see it? Everybody that's discovered will eventually go back, have a path back to the root. Okay? And the interesting thing is, once you have done breadth first search, finding the shortest path in that graph is simply a question of walking back through these parent pointers till you get back to the root. How many people see it? Okay, any questions? Okay, I still have a couple minutes actually, so I can actually be a little bit more leisurely here. Any questions here? Okay. So what should be yeah, question. Why is it I plus 1? Suppose you are I am a distance of 17 from the root, and you are a distance of 1 to me. How close are you to the root? 17 plus 1, right? If the shortest path to the root lies through me, and I am 17 from the root, and you are neighbors of me, that defines a path of 17 plus 1, right? The 1 hop to me, plus the 17 by popping back over the parent pointers. Does everybody see that? So what's neat about it, because of, and this requires some thinking about it, because breadth-first search uses the FIFO queue, it's processing vertices in terms of increasingly their distance from the root in an unweighted graph. And therefore, when I discover you, you are being discovered by the vertex of all the ones that are adjacent to you, which is closest to the root. That means that discovery relationship defines the shortest path between you and the root. Any questions about it? Okay. So how do you find the shortest path once you have the parent thing? The right way to do it, if you want to find the shortest path between vertex J and the root, you go to vertex J and go to its parent and say, is that parent the root? No. Then what is the parent of that one? Is that the root? No. And keep going till you get to the root. That walking backwards would define the path. Any questions? Yes?
Does there exist a modification for weighted graphs or not?
Does there exist a modification for weighted graphs? The answer is there exists another algorithm that is wildly different, called Dijkstra's algorithm, that works for weighted graphs. Okay? But for unweighted graphs, breadth-first search is the right way to do it. Yes? This is a correct algorithm for finding the minimum number of hops from you to me. Now, why is it right? Let's make sure we understand it right. The important thing is that because we are exploring all of my edges of the root before we explore anybody that got discovered, and because we are processing them by a FIFO queue, the vertices are being processed in order of their distance from the root. Okay? The root was the first one. It's distance 0 from the root. All the vertices that are of distance 1 from the root will be processed before any vertex of distance 2 from the root. Okay? Therefore, when you are being discovered, you are being discovered by, of all your neighbors, the one that is closest to the root.